All right, good morning, Welton ladies. Welcome back. Welcome back to College Algebra. Today we're going to continue talking about rational functions. We're also going to talk about some radical functions, and we're going to do an activity that has us playing around with rational functions and polynomial functions. So that is the rough game plan. Let's get in here and actually begin. The associated homework, I did get an email. I haven't had a chance to respond to the email, and I apologize for that. But yeah, I am extending the homework. So we haven't talked much about radical functions yet. We did talk about them a little bit when we talked about power functions, but we haven't given them their own special treatment yet. And we also haven't talked much about rational functions besides defining them and kind of drawing a picture and saying, you know, okay, this is what asymptotes look like. But yeah, clearly we need to talk about those things more. So I've extended that homework to Thursday for now, and may extend it further, but probably not. I think we'll be good on that after today. So let's do the thing. This is MAC1105, section 015, which is college algebra. And the date today is a funny one. It's 2/22/22. And I saw something cute this morning. It's also a Tuesday. So it's Tuesday 2/22/22, where it's the Tuesday. Sorry. Okay. So today we're going to finish talking about rational functions. And we'll talk about radical functions as their own thing. And then we're going to do activity 4. I did put in the activity 3 grades. Let me go ahead and set our timer to remind us to switch over to the activity at the appropriate moment. It's a 75-minute class with 55 minutes in the switch. So last time we did introduce rational functions. We talked about what rational functions are, and we looked at just one little example. And then I told you how to find the things called vertical asymptotes, the places where the function kind of blows up. Today we're going to talk about the other sort of graph features of rational functions, and I'll go through how to find and plot those. So say recall. Rational functions are ratios, known as fractions, the top and bottom are both polynomials. All right, so this is a definition we've seen a few times, and the idea that the numerator and denominator need to be polynomials means if you want to check if something is or is not a rational function, you need to check if the top is a polynomial, meaning it has only positive integer powers of x, constants, and you need to check if the bottom is a polynomial. Last time, we talked about how to find the domain. So for a rational function, we like to find the domain, and we said how we're going to do this. You're going to set the bottom equal to 0. Those numbers which make the bottom equal 0 are the numbers which are not in the domain. And this isn't actually anything fresh. This is something we talked about way back at the beginning of the class when we introduced the concept of domain red flags. Variables downstairs are a domain red flag. since the bottom is a polynomial, you expect to encounter some variables downstairs. And so the way you find your domain is just by making sure that you stay away from any places that make the bottom 0. We talked about how to find the vertical asymptotes. And this you take the solutions. These will be the lines x equals c, where c is a solution to the bottom equals 0. So in other words, those numbers that you found when you were looking for the domain, the solutions to the equation that you get when you set the bottom equal to 0, those are your vertical asymptotes. Things we have not talked about yet are x and y intercepts. So we will talk about those. And also the thing called the horizontal asymptote. So if you have these things, if you have the domain, the vertical asymptote, x and y intercepts, and the horizontal asymptote, then you can sketch a pretty good graph of a rational function, at least the rational functions that, that we're going to play with in this class. So x-intercepts. I want you to think along with me because I do think it will help you to understand why the procedure is what it is. If we're looking at a rational function, something like r of x equals p of x over q of x, where p and q are both polynomials, how would you find an x-intercept? What does an x-intercept mean in terms of the function?
Domain,
Have a thought or an opinion on this?
Is it our domain?
So definitely it's true that the x-intercepts would have to be numbers that are in the domain, right? The x values at the x-intercept should be x values of points on the graph. But finding the domain on its own isn't going to help us find the x-intercepts. In general, for a function, x-intercepts are going to be located at the x values where the function is equal to 0, right? Like the whole function is equal to 0. So these are going to come from r of x equals 0. We take the whole function, the whole fraction, and set it equal to 0. But there's a shortcut here. If r of x is this fraction, p of x over q of x, when are fractions 0, right? Like in order for a fraction to be equal to 0, what can you tell me about the top and bottom, the values of the top and the value of the bottom? So this does tie into what we were saying about the domain a minute ago, right? You know, that with a fraction, the bottom is not allowed to be 0. If the bottom is 0, we're in trouble. The thing is undefined. What about when the top is 0, like 0 over 5 or 0 over 2 or 0 over pi?
Wouldn't that still be 0 though?
Yeah, exactly. So if you're trying to find the x-intercepts, that means you're trying to solve the equation r of x equals 0. And this can be done by just setting the top equal to 0. That's all, right? So if you're looking for the x-intercepts for a rational function, finding the x-intercepts for any function means setting the whole function equal to 0. But for rational functions, because they're always these big fractions, I don't care so much what the bottom is doing. I just want to make sure that the top is equal to 0. As long as the top is equal to 0, then the whole fraction will be 0, right? Because 0 divided by any non-zero number is going to be 0. So again, the x-intercepts, you find those by setting the top equal to 0.
So for the domain, we solve for the denominator, and for x-intercepts, we set the numerator to 0.
Correct. Yep. Yeah, when we're looking for the domain, we'll set the bottom equal to 0. Whatever numbers we get from that, we're going to kick out of the domain. So it'll be all real numbers except for those things. And then if we're looking for x-intercepts, we set the top equal to 0. And the solutions to that equation will be the x values of the x-intercepts. Y-intercepts, this is the same for every function in the universe. You just plug in x equals 0. Because the y-axis is the set of all points in the plane whose x-coordinate is 0. So if you want to know where does my function touch the y-axis, you just need to plug in 0 for x. And then the horizontal asymptote, this is a slightly more complicated animal. We have a 3-case rule, which I'll outline below. Remember, a rational function is a ratio of polynomials, and every polynomial has a number associated with it called the degree. The rule for finding horizontal asymptotes is based around the degree of the top compared to the degree of the bottom. If the degree of the top is less than the degree of the bottom, then the horizontal asymptote, which I'm just going to abbreviate as HA, is the line y equals 0. Right? Just like vertical asymptotes are like x equals a constant, because they're vertical lines, horizontal asymptotes will always be y equals a constant, because they are horizontal lines. If the degree of the top is bigger than the degree of the bottom, then there isn't a horizontal asymptote. And then the fun case is when the degree of the top is equal to the degree of the bottom. And in this case, like if the top and bottom are both quadratics, or if the top and bottom are both linear functions, in this case, then your horizontal asymptote, I'm going to write this down in words because there's no clean way to write it in symbols, is the line y equals, this pen sucks, no, not that. It's the line y equals two nice black Tyler G2s, none of them want to work. The ratio of lead coefficients so the top and bottom are both polynomials, which means they have degrees, so that's why we can compare the degree of the top and the bottom. Polynomials also have lead coefficients, right? That's the number attached to the largest power of x. So if the top and bottom are both, say, quadratic polynomials, polynomials of degree 2, then the degree of the top and the degree of the bottom would be equal to each other. That would tell you that your horizontal asymptote is the line that you get by setting y equal to the fraction where the top is the number attached to the x squared there, and the bottom is the number attached to the x squared there. That's the game. Cool. So the first two things here, we had talked about these before. The rest of these are new. And this is your like Bible or algorithm or whatever you want to call it for graphing a rational function. If you want to sketch the graph of a rational function, this is how we do it. And beyond that, this is how you infer things about graphs of rational functions. So let's do one quick example where we're going to cook this stuff up and sketch a graph. We can verify on our graphing calculator. And then let's look at some kind of more critical questions we can ask ourselves based on this knowledge. So it's not just how to graph, it's also how to infer about the function from the graph. What I'm saying is make sure this shit is nice and clear in your notes. Any questions on what's written here? Okay. So use the guidelines we just discussed to sketch the graph of the rational function r of x equals 2x minus 6 divided by x plus 2. This is first a rational function because the top and bottom are both polynomials. They're both linear functions or polynomials of degree 1. And we will use that information down the road. But for now, let's go ahead and we'll just do these things in order. So first we're going to find the domain. And to do this, we're going to set the bottom equal to 0. So the bottom here is x plus 2. So I'm going to set x plus 2 equal to 0. Subtracting 2 from both sides, I just get x equals negative 2. So this tells me two different things at once. It tells me that the domain does not include the number negative 2, and it also tells me the vertical asymptote. So the domain is several different ways to say this. All real numbers except x equals negative 2. And if I want to write that in interval notation, that is the same as negative infinity up to negative 2 unioned with negative 2 to infinity. So you remember our very first activity had us taking sets described like this and writing them in interval notation. One of the reasons we did that was so you would be ready for this stuff now. The other thing we just learned is the vertical asymptote. Where these also come from setting the bottom equal to 0. So that vertical asymptote is the vertical line x equals negative 2. As we go, I'll box the individual little pieces. We want to find our x-intercept and our y-intercept. X-intercepts come from setting the top equal to 0. So here that means we'll have 2x minus 6 equals 0. Adding 6 to both sides, you get 2x equals 6. And dividing both sides by 2, you get x equals 3. So So the x-intercept has x value 3. The x-int is at x equals 3, i.e. is the point 3, 0. And the y value at an x-intercept is always 0 because that's what the x-axis is. These are solutions. The x values that are solutions to the equation r of x equals 0. Y-intercept. This always comes from plugging x equals 0. So r of 0, I plug 0 in for x in this expression, I get 2 times 0 minus 6 divided by 0 plus 2, which is negative 6 over 2, which is negative 3. So you could say the y-intercept is negative 3, or more accurately, you'd say the y-intercept is the point negative 3, 0. I'm sorry, I'm so sorry. 0, negative 3. Again, we find it by plugging in x equals 0. That means the x coordinate there is always going to be 0. Questions so far? All right, these are all things you will have to do on a test. So don't be shy. If you've got questions, I want to hear what you're thinking. Do you have any comments? Anything at all?
Vertical asymptote, we
So these, we kind of learn these along with the domain. So the vertical asymptote will be the vertical line x equals some number, where that number or those numbers are the numbers you find by setting the bottom equal to 0. So this guy, the reason I didn't have to do anything extra for him, he came straight from the work we did with the domain. So both the domain and the vertical asymptote come from setting the bottom equal to 0.
we don't have a horizontal asymptote.
I just haven't found it yet. So we're getting there. We're not. I wanted to pause and ask about these things because the horizontal asymptote rule is a little bit complicated, and we want to make sure we're comfy with this before we do that. But this function does have a horizontal asymptote. So before we get to the horizontal asymptote, any other questions or comments on these steps that we've done so far? Again, this is something you're going to have to do on the test. Okay. So yeah, our last step here is to find the horizontal asymptote. And this requires us remembering that 3-case rule. So remember what that 3-case rule says. If the degree of the top is smaller than the degree of the bottom, then the horizontal asymptote is the line y equals 0. If the degree of the top is bigger than the degree of the bottom, then there is no horizontal asymptote. And if the degree of the top is equal to the degree of the bottom, if they're the same, then the horizontal asymptote is found by taking the ratio of lead coefficients. So looking at this function, what is the degree of the top?
1.
Good. And the degree of the bottom?
Also 1.
Good. Yeah, those are both degree 1 polynomials. Right? Those are both linear polynomials. So, because these are the same, that tells us that the horizontal asymptote is the line y equals the ratio of lead coefficients, which is, so ratio means fraction, right? So I'm going to start by just saying, okay, this line is going to be y equals some fraction. The numerator is going to be the lead coefficient of the function in the top, the polynomial in the top. So what is the lead coefficient of 2x minus 6?
2.
2, right? The largest power of x here is x to the 1. So the lead coefficient is the number attached to that, which is 2. And the lead coefficient of the polynomial downstairs here?
1.
Very good. Yeah, it's the number attached to the x. And you know, if there's not anything written here, that means it's a 1. So our horizontal asymptote is the line y equals 2 over 1. Nobody would write it like that, but it's just y equals 2. So these are all the things: the domain, vertical asymptote, x-intercept, y-intercept, and horizontal asymptote. And this is always how we find them. These rules will work. They will not just work here, they will work in pre-calc, they will work in calc 1. And anytime you're asked a question about a rational function, you can think about these rules to answer it. All right, we found the stuff. Let's use the stuff to draw the graph. So the way I like to do this, think of your asymptotes as like a skeleton. So first we'll draw our coordinate axes. And then we want to drop in our asymptotes. Because again, they're sort of like a skeleton that we're going to build the graph around. The line y equals 2, I can come up here, 1, 2, is a horizontal line. And we draw the asymptotes as dotted lines. The graphing calculator will sometimes draw in the asymptotes as solid lines. Don't do that. That can be very misleading. They are not a part of the graph. So we draw in the line and we label it. Same for the vertical asymptote. The vertical asymptote was the line x equals -2. So we're going to draw in that vertical line, x equals -2, which looks like this. 1, 2. And you label it VA x equals -2. X. Then you're going to add in the points that we know. So far, the only points that we know for sure are the x-intercept and the y-intercept. I know that the y-intercept is the point 0, -3. So I can go, okay, down 1, 2, 3. There's my y-intercept. My x-intercept is the point 3, 0. So I can come over here, 1, 2, 3. Here's my x-intercept. And then we want to ask ourselves, well, what does the rest of the graph look like? This really isn't a whole lot to go on. You can make a table to plot a few extra points. Your graphing calculator can be very helpful for doing that very quickly. Or of course, you could just glance at your graphing calculator and see what the general shape looks like. Let me do this in a good spirit here. I'm going to type y1 equals. Make sure you put the top and bottom in parentheses. Number one graphing calculator mistake in general is insufficient parentheses. So top and bottom of the fraction go in parentheses. Parentheses 2 x minus 6 close parentheses divided by open parentheses x plus 2 close parentheses. Who remembers how to get a table?
Second, then graph.
Excellent. We're going to hit the button second here, and then we're going to hit the button graph here. And if you forget, remember this, the blue lettering tells you what's going to do if you hit second and then that button. So it says in blue here, table. So if I hit second, then graph, blam, there's a table. And we see some of the points we already knew, right? Like 0, -3 and 3, 0. We can hunt around for some nice looking points. Yeah, here's one, 8, 1 is on this graph. So 1, 2, 3, 4, 5, 6, 7, 8, 8, 1 is a point on this graph. So it's starting to look like I've got something like this going on over here. We can try looking maybe around -1. See what we get there. So we can scroll back to -1. Ooh, -1, -8 is on the graph. That's going to be like way down here. We can just plop them in and put a label on him so people know what we're talking about. So the portion of the graph that is over here looks like this. And it's going to get closer and closer and closer to these asymptotes as we wander and either further and further to the right here. It's going to get closer and closer to this horizontal asymptote. As we get closer and closer to -2 over here, it's going to go down like this. There's a portion of the graph over here also, and it's hard to draw it to scale, but it looks like this. And you could plot some points over here also if you wanted, but this would be great. This would be a wonderful drawing, 10 out of 10. The only things that we need to do is label these points. This is 0, -3, this is 3, 0. And I think a good standard rule is to label at least 3 points explicitly. So if you also have this labeled as 8, 1, or if you have this labeled as -1, 8, either of those two extra points would be sufficient. Finally, you can take a look at the graph in your calculator and verify that he looks how we think he does. Indeed, right? Notice this 84 is a clever calculator. It's not drawing in the asymptotes, but if you're using an 83 or a non-plus version of the 84 or some other versions, you will see this line drawn in as a solid line, and that should not be there. That's not a part of the graph. Any questions about how we got this picture? Okay, I'm going to make one more comment here, and I think this will help you with a lot of the graphing problems. The graph shape above is similar to the graph y equals 1 over x. And when we talked about power functions, 1 over x was one of the graphs that we looked at there. That graph is it's like this. Not only is the graph we just drew similar to this, so are graphs of any rational function where the top and bottom are both degree 1. So if you're looking at a rational function where the top and bottom are both linear, they will all have this same sort of shape. It's called a hyperbola. You'll have one vertical asymptote and one horizontal asymptote. It might look like this guy, where the branch is kind of down here in the bottom right quadrant. Or it might look like this guy, where this branch is up here in the top right quadrant. But it will always be the same basic shape, right? Just like all quadratics have that same basic shape of a parabola, all rational functions where the top and bottom are both degree 1 will have this same basic shape, which is called a hyperbola. Okay. There are some kind of clever questions in your homework about these things. Let's take a look at one or two of those, and then we're going to talk about radical functions briefly. One of my favorite things is to ask you to construct a rational function with certain features. Domain is this in the ground. Interval notation, use the domain interval notation, describe all the equation for horizontal asymptote. I think he gets a little bit sneakier than this. Oh, maybe not. Yeah, I thought maybe he pulled them out. Let's some like construct this from no, okay, well, it's not the case. Okay. Yeah, so for the things that we're asking you guys about in the rational function section here, really everything you need is what we've done so far. The set builder notation for the domain is the one thing that I'm seeing there that we haven't talked about explicitly. So there is an alternate notation for the domains. If I want to describe all real numbers except the one we did above, except x equals -2, we can do that in words like this. We can do that in interval notation like we did as we found the domain there. You can also write this in what's called set builder notation. So the way you read this notation on the right is the set of all x's. This vertical line means such that, and then it says x is not equal to -2. So this is the set of all numbers x such that x is not equal to -2. And here you put your conditions. That's how you read this. It is the set of all x's such that x is not -2. Before we move into the radical stuff, just really quick, let's see if we can find the domain of a more complicated rational function and express it in this notation. Here's another rational function. This time the degree of the top and bottom are both 2. We could go hunting for all that stuff, but I'm just trying to find the domain. And we're going to give the answer and we set builder notation. Early braces notation that we just in. So how do I do it? How do I find the domain?
Put the factor out the bottom first.
Good, yeah. The thing here is to set the bottom to 0, and to do that, we're going to want to factor the bottom. So we start by just saying we're going to set the bottom equal to 0. That means we're setting x squared plus x minus 6 equal to 0. And then the way we solve this equation is by factoring, right? This quadratic factors nicely. Looking for two numbers that multiply to -6 and add up to +1. That would be x plus 3. And x minus 2. So the two solutions to this equation, bottom equals 0, are x equals -3, +2. This tells me that my domain is all real numbers except for these guys, right? All real numbers except for the numbers that make the bottom 0. And if I want to put this in the set builder notation, that's the set of all x's such that x is not equal to -3 or 2. You can write it like this. Or you could write x not equal to -3, x not equal to -2 separately. Either one is fine. The set builder notation is a very convenient notation for the domain of rational functions because their domains always look like this. It's always all real numbers except for a few of them, except for the ones that make the bottom 0. And it's easier to write those in set builder than it is in interval notation. But, if the problem doesn't specify, either way is fine. Okay. Rational functions, these are fun things just for gets and shootles. Let's take a quick peek at the graph. I expect vertical asymptotes at -3 and 2. I expect an x-intercept at 0 because that's when the top is equal to 0, which tells me that my x and y-intercept are the same point, i.e. this goes through the origin. And I expect a horizontal asymptote to be the line y equals 1. Let's see what we get. Again, tops and bottoms in parentheses is good discipline. Let's use x squared down close divided by parentheses. X squared plus x minus 6 close parentheses. There's the vertical asymptote at -3. There's the vertical asymptote at +2. And the horizontal asymptote would be the line y equals 1. So we could, if we wanted to, a really quick graph sketch here. It would not be a long-term process. So, first VA. Second VA. We have a piece of something like this in the middle. And then we have a horizontal asymptote. little branches here. So HA, 1 equals 1, UVA, 2. And then the point we know for sure is on the same right now as the origin. Let's put A. Right. If you're just trying to get a feel for the graph, you're just trying to sketch it, this would be fine. Not so painful, right? As long as you know where things go, and where they come from, it can be done very, very quickly, especially with the help of the graphing calculator. So that's it for us on rational functions. Radical functions are things that we've discussed in the past when we talked about power functions, but they deserve a little bit of unique treatment here. They kind of sound similar, rational and radical, but the truth is they're very, very different animals. Radical functions are just functions involving the radical symbol. So functions of the form f of x equals some root of some other function. And that root could be a square root, could be a cube root, could be a fifth root, could be a 12th root. G of x could be linear, quadratic, could just be x, could be a lot of different things. If g of x is just x, then we're talking about a power function. When you're talking about just the nth root of x, which is the same as x to the 1 over n, it's a power function. And these we studied previously. So you know the rough graph shapes for all of those guys, right? If this would be a power that is positive, and between 0 and 1, we know that their graphs look like there's kind of two possibilities. If it's an even root, it'll look something like this. Or if it's an odd root, it'll look like that same picture in the first quadrant, but then they have that kind of serpentine squiggle shape in quadrant 3. This is if n is even. And this is if n is odd. And we're not going to push you guys terribly hard in this direction. Most of the radical functions that we're interested in either g of x will just be x, that is the thing underneath the radical will just be x, or it'll be some linear function, which means the graph shape will still be one of these guys, but the domain will be different. The graph will be kind of shifted to the left or to the right, something like that. So the big game is to know these two basic graph shapes, and then being comfortable kind of dragging them to the right or the left according to how the thing under the radical looks. So let me remind you, one of our domain red flags from earlier in the semester is going to come up here. We said if you have variables under an even root, then you need to make sure that that stuff under the radical is greater than or equal to 0. So if the root is even, like n equals 2 or 4 or 6, then to find the domain, you need to set the inside, which is the thing we call g of x up here, greater than or equal to 0. And the place where the inside, or g of x, is equal to 0 will also kind of tell you this starting point, if you like. I think I hear people call it that a lot. Or this kind of like saddle point, or the place where this thing does its little squiggle. Because if the inside here is 0, if g of x is equal to 0, that's the x-intercept. And these only have one x-intercept. So let's grab something out of your homework. Let's grab one of these that looks a little scary and see if we can do it. So we want to find the domain and the range of this guy. That sounds fun. So it's y equals square root of negative x plus 1 minus 6. Finding domains is relatively easy. To find the range, you need to know the graph. Minus 6, right? So what we have here is something looking like the square root of some simple function. Then we also have this minus 6. Now, this isn't going to have any impact on the domain, but it will have an impact on the range. If you come see me in pre-calculus, I'll tell you exactly how to graph these sort of things by hand, because in that class we take away the graphing calculator. But what we're going to do here is find the domain by hand using our domain rule. And then we're going to take a look at the graph in the graphing calculator and use that to sketch the graph and infer the range. Domain, we use the rule. The range. We look at the graph. And you can use the calculator for this. You could also try to infer the domain from the graph. But there are plenty of problems where you won't be able to read the domain off from the graph nicely if I involve some weird decimals or fractions. So it is important that you are comfortable finding the domain using pencil and paperwork. The root here is a square root. So we need to solve the inside is greater than or equal to 0. The idea here is that you don't want to take the square root of a negative number. So this function will be happy as long as the thing under the square root is greater than or equal to 0. Being 0 is okay. The square root of 0 is 0, no problems there. This does, however, mean that you got to solve an inequality. This is negative x plus 1 is greater than or equal to 0. These inequalities can be easy, they can be hard. We have some practice with inequalities in the past. Several ways you could solve this. You can subtract 1 from both sides. That will give you negative x is greater than or equal to negative 1. And then you can divide both sides by -1. And when you do that, the sense of the inequality, the direction it's pointing, flips over. We're multiplying or dividing by a negative, flips the inequality. So we solved the inequality inside greater than or equal to 0, and we got x is less than or equal to 1. In other words, the domain here is the set -infinity up to and including 1. That is this inequality as an interval. Any questions on this domain finding procedure? Start with how we knew to set up this inequality. Or any
Did you
questions?
forget about the 6?
That's true, yeah. So I'm not worried about the 6 at all here, because our domain rule just says, look at the radical part, right? If the inside has some variables and the radical is an even root, then you need to set the inside of the radical greater than or equal to 0. So it's true, this 6 doesn't have any effect on the domain, and that might be a little counterintuitive. Kind of the thing I recommend when you're thinking about domains for expressions in general is ask, how could you upset this expression? How can you make this thing angry? The only way to make a function like this angry is if you ask it to take the square root of a negative, right? What you're plugging in for x this 6 doesn't care about that, right? This guy has no feelings one way or another about what you're plugging in for x. The only part of this expression that cares what x is the radical. And this radical will be happy as long as the stuff underneath is not negative and greater than or equal to 0. So we just set the inside of the radical greater than or equal to 0. If this was a cube root, then we wouldn't have anything to do. So we only even need to worry about this stuff if the root is an even root. So square roots, fourth roots, sixth roots, etc. Cube roots, they don't care. The inside can be negative, positive, or 0. So if this was a cube root, automatically we would know our domain is all real numbers. Let's take a look at the graph. And here to y equals clear. We can type square root by hitting second and this squaring button, because you see the little blue square root there. And then remember, the negative button is this one. This is minus, it's an operation. Negative down here, x plus 1. And then you want to hit the arrow to get out of the square root. So hit the arrow right to get out of the square root, and then type the -6. See what that graph looks like. Interesting. It almost looks like it's a straight line, but it's not. I promised you that the graph shapes will always be one of these. And since we're having an even root here, the graph shape is this guy. It's just been flipped over and then dragged down. So a graph here. I know 1 is an important x value because that's where my domain stops, right? We go from -infinity up to 1. We can take a look at a table. And what we see is when x is bigger than 1, we're getting errors because these numbers are not in the domain. When x is exactly equal to 1, y is -6. So the point mark down here, when x is equal to 1 is 1 comma -6. And then looking at the picture, we see, oh yeah, it's that square root shape. It's just pointing to the left. And I like to exaggerate these a little bit when I draw them. Something like this. Now we can deduce the range. And this guy, like all of those shapes, he continues going on and on and on like this forever. In particular, he does poke up through the x-axis. So my range is going to be the set of all y values on this graph. And this guy continues going up and up and up and up forever. So my range here all these y values. Remember, we play the swooshing game. You swoosh the graph onto the y-axis. And because this piece does go up and up and up forever, the range will go up and up and up forever. So the range would be interval from -6 all the way up to infinity. And that's it. So your domain and your range. And don't be shy about using the graphing calculator. Don't be shy about changing the window settings and moving your picture around to help you see things. Don't be shy about using the table. If you're not sure that that range ever goes up past 0, take a look at this table and see what happens if we keep scrolling. See over here, keep scrolling back this way. Do we ever get to some positive numbers? It's going to take a while, but sure, here we go. By the time x is in the -40s, we're looking at positive y values. And so keep going deeper into the negative x values, those y values keep going up and up and up, and they will eventually go to positive infinity. There's no upper bound for this guy. You can use tools like Desmos. I know it's easier to zoom in and zoom out on Desmos, and that's fine. Just remember that when it comes to the test, you're only going to have the graphing calculator here. So make sure that you're comfortable doing in the graphing calculator the things that you're comfortable doing in Desmos. I'm going to go ahead and sort us into breakout rooms so we have time to finish that activity. If you have not done so, please open, or ideally you've already printed this, but take a look at this activity. Make sure you have this saved somewhere. You can view the problems. You can click that and then open it or save it. I would recommend saving it, whichever one you want. We're going to sketch the graph of a rational function by finding the domain, vertical asymptote, x-intercepts, y-intercepts, and horizontal asymptote, and then plop in your graph. And then I have some polynomials for us to play with. So I give you here the factored form of a polynomial, and I want you to tell me the roots, the multiplicity of those roots, remember from last time, and tell whether the graph is going to bounce or cross the x-axis at each of those roots. The last problem, I have here another polynomial, only this time I haven't factored it for you. So you need to factor the polynomial to find the roots here. You're going to do the same thing. You're going to factor this, tell me the roots, the multiplicity, and whether the graph bounces or crosses the x-axis at each of those roots. And then there's a few little questions for each of these. So you can tell me if you see any local mins or local maxes. Tell me where the function is increasing or decreasing. And on the previous guy, after you draw your graph, you can tell me where is f of x positive, greater than 0? Where is f of x negative, less than 0? And what are the solutions to the equation f of x equals 0? So those are meant to be done from the graph. So first step is to draw the graph. Okay, I'm gonna sort you guys into breakout rooms, and I'll come in and check on your progress. We've got 20 people here. 4 rooms. Once you receive the invite, please go ahead and join. Ooh. Oh, that's so nice. Thank you, sweetheart. Gabriella, Emily, Ariana, you guys here? Okay, I can't give you credit for the activity unless you guys play along. If you are here, please go ahead and join that room and help your group. Alrighty, hey guys, how's it going?
Meeting is being recorded.
Good. We're talking about the first problem.
Okay, is there anything you'd like a little bit of help or a nudge with to get started?
I think we're getting it.
I just have one question.
Yeah, go ahead.
Is the vertical asymptote always going to be what the domain is? Because our domain was 1, so is the vertical 1?
It's true that you find the vertical asymptote at the same time as you find the domain. So your domain is going to be all real numbers except 1, because that's what makes the bottom 0, right? That's the number you can't plug in. And that tells you at the same time that your vertical asymptote is the line x equals 1. So I would say just pay attention to how you're describing these things. You're right. Yes, 1 is the number that's relevant for both of those.
Okay.
So because the way I would write this is because when you set the bottom equal to 0, that is x minus 1 equals 0, which is x equals 1. And this tells us all at once two things, that the domain is all real numbers except 1. And if we want to put that in the set builder notation, that would be the set of all x such that x is not equal to 1. That's a nice way to describe that. And it also tells us that our vertical asymptote, and I'd be careful about this because the, the committee that designs the final exam for this class is very picky about this. The vertical asymptote, they want that as an equation. So don't just say 1, it's the line x equals 1.
Okay, thank you.
Yeah, of course. All right, I'll let you guys work for a little bit longer and then I'll come back and check. Hey there, guys, how's it going?
Good. We're just checking our answers.
Okay, is there anything that
We're going over 1, but I had a question. So I figured out everything. Like I figured out the domain, the isotope, the roots, and the y-intercept and the horizontal, and I graphed it all out. But how do I draw like, how do I find another point so I could draw the curve?
There's a few options there. You can either make a table by hand by plugging in a bunch of x values and seeing what y values you get out. That takes a lot of time though. So my suggestion would be to either use the table function on the graphing calculator. So we could come in here, go to y equals, and type, what was our guy? 2x plus 4 over x minus 1. So paren 2x plus 4 closed above paren x plus 1 closed. You can hit second and graph to pull up a table, and this will give you a bunch of points. Now I'm way down here from our earlier example. These would be silly values to use because they're way way outside where we normally look, but yeah, we can look at any nice values from this table to conjure a point. And if you wanting like extra points like 3, -1 would be nice. 2, 0, presumably you already found, that's your x-intercept. 0, 4, that's your y-intercept. You can go with 1, 3 for your extra point, or -3, 1. Most of these are going to be a little bit gnarly from there on. The other thing you can do to help yourself kind of get a feeling for the shape of the graph is to just look at how this thing draws the graph. So it should look like that. And then you can pull out an extra nice point or two from the table. Does that feel comfy?
Okay, yeah, that makes a little bit more sense.
Cool. And then the one bit of caution I would have here is that in those first few steps where you're finding the domain and the vertical asymptote, make sure that you pick a notation that you're comfortable with for the domain. You can either use the set builder notation like this, or you could use interval notation. In interval notation, this would be -∞ to 1 union with 1 to infinity, all parentheses. But I think the set builder is a really nice way to do it. Just make sure that you're writing all the little bits here. The last thing is that the committee that writes the final exam for this class is extremely picky about how you describe asymptotes. So I know it's tempting to say the asymptote, the vertical asymptote is 1. And if you said that, I would know what you're saying, but the way the committee structures the final, that will still end up getting marked wrong. So we need to be a little bit more specific. We always need to give the equation of the line. So the vertical asymptote is the line x equals 1. I know it seems like a really silly distinction, but just trust me, the folks who designed the final for this class are very picky about that. So I think it's a good idea to practice it that way also. So when you describe your domain, make sure you're writing one of these two things. And when you describe your vertical asymptote, make sure it's x equals 1 instead of just 1. And the same sort of thing is true for the horizontal asymptote here. We would want to make sure we describe the horizontal asymptote as the line y equals 2, not just saying 2. Is there anything else that you guys want to talk about real quick? Well, we've got a second.
For problem 2, when it's like the first part is -x to the third, is that just -1?
So the negative here means that the lead coefficient is -1. That's true. And then the x cubed, we can think of that as that -x cubed. And then what were the other two factors here?
X minus 2 and then x plus 2.
Thank you. So when we're trying to sort out the roots, I would think of this x cubed as x minus 0 all cubed. And that your x minus 2 and your x plus 2. So the roots come from setting each factor equal to 0. Hi, baby, I love you. So here we'll have a root x equals 0. Here we'll have a root x equals 2. And here we'll have a root x equals -2. And the multiplicity is the power of the factors. So the multiplicity here would be 3. And the multiplicity for these guys would both be 1. And those multiplicities being even or odd is how we know if the graph crosses or bounces off the x-axis. So these are all odd multiplicity, which tells us that the graph will cross the x-axis at each of those points.
Okay, thank you.
All right, I'm gonna go check on the other rooms. I'll be right back. Alrighty, how are we doing, guys?
Doing okay.
Is there anything that you'd like to talk about, ask about, look at together?
How about the bounce across?
Are we looking at problem 2 or problem 3?
2.
Okay, so let me turn on my share here. So when it comes to this guy, first thing I would do is just write down this polynomial, right? the trick to figuring out whether we're going to bounce or cross is first, of course, find the roots. So we can write this negative x cubed as negative x minus 0 all cubed. And then we find the roots by setting each factor equal to 0. So if x minus 0 is equal to 0, then that gives you the root x equals 0. Setting x minus 2 equal to 0 gives you the root x equals 2. Setting x plus 2 equal to 0 gives you the root negative 2. And then the trick to the bounce or cross thing is the multiplicity. We need to know whether the multiplicity is even or odd. Remember, the multiplicity is the power of the factor. So if we look at the factor that gave me the root x equals 0, that's this factor. And the power of that factor is 3, right? That's the x cubed here. So the power is 3. That means the multiplicity is 3. And then each of these other guys, if there's no power written there, remember that's the same as having a power of 1. So the multiplicity of each of these guys is 1. And then if the multiplicity is even, you will bounce. If the multiplicity is odd, you will cross. So each of these multiplicities, 3, 1, and 1, are all odd. So we will cross at all of these. Does that feel comfy?
Yeah, it looks good. Will you go over problem 1?
Sure. So the first thing we want to do there is find our domain and vertical asymptote. Both of those come from setting the bottom equal to 0. The bottom there is x minus 1. So if we set x minus 1 equal to 0, we get x equals 1. And then from that, we get both the domain and the vertical asymptote. Since this fraction will be undefined when its bottom is 0, and its bottom is 0 when x is equal to 1, we know that our function is undefined when x is equal to 1. And that means that our domain is all real numbers except x equals 1. And there's kind of two acceptable ways to write that. You can write that in interval notation as negative infinity to 1, union with 1 to infinity, where all the things are parentheses. Or, and I think the nice thing here is for rational functions, it's very, very nice to write the domain in set builder. So this is the set of all numbers x such that x is different from or not equal to 1. So I think this is probably how I would write the domain. And the other thing we learned is the vertical asymptote. Remember, the vertical asymptote is going to be a vertical line. And the committee that writes the final for this class is very, very picky about how they want you to describe asymptotes. So don't just tell me that the vertical asymptote is 1. It's the line x equals 1. And they always want you to give the equation of that line. So that's the first couple parts there. The other things we need are the intercepts and the horizontal asymptote. The x-intercepts, these always come from setting the top equal to 0. And the top here was 2x plus 4, is that right? Yeah. So if we solve this for x, we get 2x equals negative 4, and then dividing both sides by 2, x equals negative 2. So the x-intercept would be the point negative 2, comma 0. The y-intercept, we always get this by plugging in x equals 0. So if I do that, we call the function r or f here, f. So f of 0 is 2 times 0 plus 4 divided by 0 minus 1, which is 4 over negative 1 or negative 4. We know that the x-coordinate there is 0, so the y-intercept is the point 0, comma, negative 4. And the last thing we would need is the horizontal asymptote. We get this by looking at the degree of the top and bottom. So the degree of the top is 1. The degree of the bottom is also 1. So since the degree of the top is equal to the degree of the bottom, we learn that the HA is the line y equals the ratio of lead coefficients. So the lead coefficient of the top is 2. The lead coefficient of the bottom is 1. So this would be the line y equals 2 over 1, or just y equals 2. And once we have all of these things, we can sketch our graph. Here's the vertical line x equals -1. Here's the horizontal line y equals 2. We can plot the points that we know, which are -2, 0. So -2, 0 is right here. And 0, -4, then 2, 3, 4, right here. This isn't a whole lot to go on though, so I think it might be nice to also take a look at the graphing calculator. Go to y equals, can type in our function. You could get more points by going to the table, right? And of course, you see tons of other points here, like -3, +1. So I can come out here, -3. -3, +1 is on the graph. We could go to -4 or something like that. We can come down here. We see that there's some really nice points. 1, 3 is on the graph. 1, 3 will be up here. So you can kind of start to get a feel for what's going on. But I think it would be most helpful to do this. So you see this piece over here. Oh, did I miscalculate my y-intercept? Is it x plus 1? Yeah, sorry, this is an x plus 1, isn't it? Plus 1, this is +4. All right. Yeah. So we can see from the picture in the graphing calculator that these 2 points are part of the curve doing this. And the 2 points up here are part of the curve doing this. And that would be 20 minutes. We just need to make sure the label is explicitly. So let's do that on the floor. -3. Not so bad, right? I do have someone in another room asking for help. I'm going to go over there and talk to them really quick, and then I'll pull us all back into the main session. Hey, Chatty, did you have a question?
Yeah, about the less than and equal that, or for question 2, do we set, I know we set the y to 0 to find if it's equal, if y is equal to 0. How do you find when it's less than or?
So having the graph will be very helpful here. So let's go ahead and see. So we had, presumably we knew already that we've got our roots and we know whether we're going to bounce or cross at each of them. So the roots were 0, -2, and I'm sorry, 0, 2, and -2 if you're going in order from the factors. So if I come over here to -2, over here to +2, I know I have roots, aka x-intercepts at these points. I know the end behavior of this polynomial is going to be up on the left and down on the right, because this is a degree 3, 4, 5 polynomial. So it's an odd degree polynomial with a negative lead coefficient, which tells me my end behavior is going to look like that. And then each of these roots is a cross. So over here, I have to come down and cross. Over here I have to cross, and over here I have to cross. So my graph has to look something like this. And you can put this into your graphing calculator if you're not 100% comfortable drawing that graph just based on what we talked about. But then to figure out where f of x is less than 0, you're asking where is the graph below the x-axis?
We can't see your screen that you're writing on.
That's not very helpful, is it? Okay, so from the factors, we learn the roots. Those are these 3 points, -2, 0, and +2. From the multiplicities, I learned that we cross at each of these roots. From the degree, which is 5, and the lead coefficient, I get the end behavior. So once I have the crosses and the end behavior, I can stitch these together. Or you could use your graphing calculator to get a nice picture here. So I could say this is -x⁻³ times parentheses x -2 times parentheses x +2. Throw that into my calculator. And we see something looking about like this. We want to know where is f of x less than 0. That's the same as asking where is the graph below the x-axis. Well, that's true here. And it's also true everywhere over here. So this would be from -2 to 0 and from 2 to infinity.
And we wouldn't put close brackets for the -2, 0, or would we?
Because we're asking, let me take a quick look at the question. Because we're asking where is f strictly less than 0, I don't want to include the points where f is equal to 0. So yeah, this would be parentheses everywhere. If this was less than or equal to, like with the equal to below it, then we would use brackets everywhere except at the infinity. Does that make sense?
Yep.
Alrighty then. I'm going to go ahead. I think we're going a little bit over time, so I'm going to pull everybody back into the main session, see if there are any questions we all want to ask together, and then wrap things up.
This meeting is being recorded.
Alrighty, guys, those breakout rooms always take a second to close. It seems like this activity is maybe a little bit more than we had time for here today, so don't panic if you didn't finish everything. Do make sure you take the time to work out these problems. There's a few things I want to share with everybody before we wrap up. The first thing is just how we like to format our answers when it comes to those questions about rational functions. So for example, in problem 1, when we're asked for the vertical asymptote and the horizontal asymptote, make sure you're always giving those as equations. So our vertical asymptote and our domain we found at the same time by setting the bottom equal to 0. When we do that, we get x equals 1. So we know that the bottom of this fraction is going to be 0 when x is 1. You can't divide by 0, right? So that tells us that our domain is all real numbers except for x equals 1, because that's what makes the bottom 0. And there's two ways you can write that down. You can write that in the set builder notation like this. Make sure you're including the curly braces in the vertical line for such that. Or you could write that in interval notation like this. Either one would be okay, but it's possible that a question requires the answer in one form or another. So make sure you practice both. The other thing you need to be careful about is describing the asymptotes. So if you just tell me that the vertical asymptote is 1, well, I would understand what you're talking about. The committee that writes the final for this class is extremely picky about how you format these answers. You need to tell me that the vertical asymptote is x equals 1, because this is the equation of a vertical line. It is an important distinction. It seems like a silly thing, and it's a little bit a silly thing, but it's not 100% a silly thing. The same thing is true of the horizontal asymptote. When you tell me the horizontal asymptote, please don't just say it's 2. Make sure you tell me it's the line y equals 2, right? Because y equals a constant is a horizontal line. The other thing that I wanted to look at a little bit together was the graph of the function in the second problem. So the way I get this, and you can get this by hand pretty quickly, although you also have your graphing calculator, you found the roots from the factors to be -2, 0, and +2. They were all odd multiplicity roots. The 0 comes from this guy, which is multiplicity 3. The +2 came from this guy, which is multiplicity 1. And the -2 came from this guy, which is also multiplicity 1. The degree of this polynomial is the sum of the multiplicities. That's 3 + 1 + 1 is 5. So that's an odd degree. And the lead coefficient is negative. That tells you that your end behavior is up on the left and down on the right, which now allows you to fill in these guys. You know you have to cross at each one, and if you're going up on the left, this cross has to go like that. You know you're coming back to this guy from below, so your cross here has to be like that. And you know you're coming down from above here, so your cross has to go like that. This is enough to draw a very reasonable graph of this polynomial. I'm putting a little squiggle in at 0 here because this is a multiplicity 3 root, not a multiplicity 1, so it should have that kind of S-curve shape there. That's not terrible. If you don't notice that, it won't hurt you. The other option, of course, is to use your graphing calculator. So if you type in this function just exactly as it's written there and hit graph, you'll get this picture, which is this picture, right? Very much the same. Once you have the graph, you can solve inequalities like f of x is less than 0. The inequality f of x is less than 0 is asking you where, or for what x values, is the graph below the x-axis, right? Remember, the y values on this graph are f of x. So if I ask you where is f of x less than 0, I'm asking where is y negative? Where is this function negative? So that would be here, where the graph is below the x-axis, and also here, where the graph is below the x-axis. That first chunk of the graph corresponds to the x values from -2 to 0. So -2 to 0 is a part of that solution. And because this is a strict inequality, we do not include either endpoints. F of x is equal to 0 at those endpoints, not strictly less than 0. Similarly, from 2 to infinity, this function is negative, right? The graph is below the x-axis, so we would include the interval 2 to infinity in that solution. I will let you go. The last thing I want to say, work problem 3. If your group didn't get to it, that's okay. Work problem 3. Just know that you need to begin by factoring. So in problem 2, I factored the polynomial for you. In problem 3, you need to factor this yourself. And the first step is going to be pulling out the GCF, which is just x. Then you'll have a quadratic left over. You can factor that and do everything the same from here. All right, I will leave it at this. It's okay if you guys didn't finish every problem, but please do spend the time to work those problems to your satisfaction. If you want to talk to me about any of it, I'll be moving into an office hour right after this. And next time, we will talk a little bit about reviewing for exam 2. Exam 2 is very, very close. I wouldn't want to push it too soon. Let me see, I think probably this upcoming Tuesday would be the best day for exam 2. So I'll make an announcement about that. And then on Thursday, we will review for the test. Right? So that is it from me. If you want to come talk to me in office hours, please do. Otherwise, I'll see you guys on Thursday.